So hello, this video is about electromotive force and internal resistance in cells. To start with, we start to define our electromotive force. So force, can't write, okay. So to start with, electromotive force, that is a very silly name because it's not a force at all. We usually have the abbreviation EMF to that, and as a symbol in our calculations we use epsilon, and we define epsilon as the work as a charge, that work that a charge can do as it moves around the circuit, and that is including the work it can do as it crosses some internal resistance and so on. Wait a minute, work, oh, that is just the voltage, right? And it is the voltage. It is the voltage, we can say it's the voltage that you have across a cell or a battery if we wouldn't have any internal resistance. Okay, so how to measure this? Say we have a circuit. We have here a cell or a battery, and it will have some kind of internal resistance. All batteries and cells do have some kind of internal resistance. Of course, it's not because of it is designed that way. It's because of that's simply how nature works, right? We can't make batteries without any resistance at all, or maybe we can one day, but anyhow, we will always have some kind of internal resistance. And if I connect this to a voltmeter, and also I will indicate that all of this is actually inside the battery or cell. Okay, so what happens now if we measure this voltage? An ideal voltmeter has an internal resistance that is infinite. And what will that do with the voltage drop over this? Oh, we just look at Ohm's law, right? R equals to V over I, which means that voltage equals to R times I, which also means that I equals to V over R. So if we have a very large resistance, the current will be very small. And if you have very small current over this resistance that is very low, that will cause a very small voltage drop. So basically you have no voltage drop across this, so the voltmeter will basically measure the voltage across the cell, so to speak, the internal voltage, and that is the EMF. Okay, so say we have a circuit here and we measure that voltage to be 1.589 volts. It's a rather typical voltage you can measure on the rather new battery, on one of these AAA batteries or something like that. They are marked with 1.5 volts, but they initially have a slightly higher voltage. And now we want to find the internal resistance. And of course we can't just put an ohm meter across this, because the ohm meter would try to measure across this battery, and that would probably not be very good for the ohm meter. So what we do is we put an external resistance across the battery. And say we put resistance here of, let's say 10 ohms to simplify our calculations. And now we look at the voltage, and we will see that that will change. So say we call this voltage that we measure now is 1.543 volts. And by the way, if you do this measurement in reality, do disconnect the resistor after a short while, because this drains the battery very quickly. This is a rather low resistance here. So given this, how could we find internal resistance? Okay, so in a problem like this, you start asking, what could I really... there's two ways to go about here. What do I need, or what can I calculate, top down or bottom up, so to speak, in our pursuit for the answer. We can start with what we can calculate. We know the voltage there, and we know the voltage across there. That means that we can calculate the voltage across this by Kirchhoff's second law, right? So what we do have here is that the internal voltage must be equal to our voltage across this minus the voltage we measured over the resistor. In this case, that will give us 0.046 volts. Okay, so what is the next thing we can calculate? Of course, we know the voltage across this, and we know the resistance, which means that we can calculate the current, right? So let's calculate the current. That would be equal to 543 divided by 10 ohms, which will give us 0.1543 amps. Of course, the precision here is ridiculous, but I keep this for the calculations. Don't round before you actually need to, so to speak. And now, of course, we know the current. That is the same current that goes through here, because none is going there, basically. This as we measured in one of the lessons, the internal resistance of the voltmeters we have at work is about 20 mega ohms. So that means that basically no current will go through there. So this current we just calculate must be the same as the current over this R1, which means that since we know the voltage over R1, that is this, we can calculate the internal resistance as the voltage divided by the current, the voltage, internal voltage over the current, which is 0.046 divided by the current, that is 0.1543, and if I did my calculation right, that should be about 0.30 ohms. So there is how to find internal resistance. How critical is the accuracy of this one? Because I think this is 0.3 ohms, shouldn't that be very accurate also in the same order? But if you think about this, if this is slightly off from 10 ohms, that will means that we will divide by something, say this is 5% off, we'll divide by something here that is 5% off, which means that this will be 5% off, which means that this will in the end up being 5% off. So that one is not so critical that this should be like super high precision. Basically the answer here will be depending on the precision at the measurements of our outer resistance. Okay, let's look at what we actually done here. We'll look at what happens if we know the internal resistance, and that means that our current through the circuit will be our EMF divided by the total resistance, right? And our voltage over the resistor will be our resistance times our current, and the current was there, so we can write this as epsilon R over R plus R internal. So we can see, if we want to make a diagram, how the voltage varies with the outer resistance. We can see here that if the outer resistance is close to 0, this will be close to 0, right? Which means that the voltage will be close to 0. So at low resistance, we have a low voltage. And if R goes towards infinity, this will approach 1, because this is doesn't really matter now. These two will be equal basically, so this will approach 1, and we will have an asymptote at E, at epsilon I mean. And we will get a graph that looks something like this. So this is the voltage we have, and this is the resistance. So we will get a graph that approach epsilon. So that is a little just extra thing here. But the key thing is how we find the internal resistance. I hope this helped a bit. Thank you. Bye.